In this video, I want to discuss why first order logic is important, and perhaps the most practical importance that it has for you in your daily lives is that it's foundational to modern day computers. Um, so computers, as you might know, run off of binary codes. So it's 1 and 0 or on and off. And where computing got that from was first order logic. And we can see this when we get to truth tables. Now, truth tables is something we're going to learn down the line, but just to give you a sense of what we're talking about here, we can make a table that represents statements. So let P be one of our statements. Now, a statement can be true or false. You think about the grass is green. Well, the grass is green can be true or false. Take a look outside. It's either true or it's false. So that is our 1 and our 0. That is our on or off. T or F. On or off. 1 or 0. So those are two cases that a proposition can take. But as we've seen already, we can connect our statements to other statements with certain logical connectors. So we've seen the if-then, which is the material conditional. We've also seen and or conjunction. Let's look at that one this time. We've also already seen the negation. Okay. So now that I've added Q in this case, Q can be true when P is true and when P is false, but it can also be false when P is true, and it can be false when P is false. Okay? So now we can treat these true and these falses, these cases of true and falses, as inputs into our connective, in which case our connector, what's connecting P and Q, we can treat that then as a function. So a function, it'll take, what a function does is it takes values into it, and then based on the values that get inputted into it, it outputs another value. So in case 1, we are inputting the value true and true, or in computing 1 and 1. And what a conjunction will do is that it will turn the value t, or it will return the value 1 on that case. For the way that conjunction works is anytime one of the inputs is an F, it will return an F. So 2, 3, and 4 all have inputs of F. So here's an F, here's an F, and both of them are Fs in case 4. So that'll return F or a 0 or an off in these cases. All right, so as we can see, the foundations then for computing is just mapping off of first order logic and how connectives work in it. In fact, if you're a computer science major, this probably looks very familiar to you. You have probably dealt with having particular functions that if you input a 1 or a 0 in, it's going to return something else. All right, so that's how we get modern day computers. It's also where AI is going to be built from. And with any luck, AI is not going to be taking our jobs. All right, let's take a look at the linguistic importance of first order logic. First order logic, by using symbolization, has allowed us to study our language, study natural language, and specific aspects of natural language in more detail. So we've already seen in the previous video some of the symbols that are going to be available to us. So we might, for instance, represent the sentence, if the grass is green, then it's not snowing outside. And we could represent that like so. G, arrow, handlebar, S. If the grass is green, then it's not the case that it's snowing outside. But take a sentence such as, all dogs are mammals. With that, we end up symbolizing it with the universal quantifier, and we're going to have predicates this time. So if for everything, for all x, we find out that an x in question is a dog, then it's a mammal. And part of what's interesting about this is this symbolization reveals to us that this universal quantification, all dogs are mammals, actually takes this if-then structure in it. So it's that if-then structure, or what we call a material conditional, is built into a universal proposition such as all dogs are mammal. And that's not obvious without this symbolization. So that's one way in which first order logic has allowed us to study language a little bit better and a little bit more clear. By the same token, it allows us to be more clear in what it is that we're expressing, and that's a feature that's important specifically to philosophers. Talking about philosophers, let's now move on to the philosophical importance of first order logic. First order logic is important to philosophy because philosophy employs logical argumentation in trying to establish particular positions or theories or whatever the case might be. So whether that's an ethical theory, whether that's metaphysics, whether it's epistemology, so on and so forth. But we don't just get to do good philosophy. We don't just get to assert any old theory that we might want to assert. We actually need to provide reasons for thinking that it's true, and we need the reasons that we offer for thinking that it's true to actually support the position that we're offering. So in that way, first order logic provides us a means for doing that. So let's look at that a little bit more in depth. So deep down, a logical argument is something that attempts to establish a position by offering evidence that is intended to support that position, the position in question. The evidence we end up calling premises. So whatever it is that you lay out as your evidence, that's your premises, and then the position that's supposed to be supported by the premises, that's our conclusion. But even though somebody gives you reasons, gives you evidence for a position, that doesn't mean that they're right, that the evidence they're offering secures the conclusion. So there's this outstanding question of whether the evidence actually supports the position or whether it merely appears to do so. All right, so how do we decide when a deductive argument, when the evidence that's given in a deductive argument actually supports the conclusion? Well, if you think about what it is that you're doing when you give an argument or when somebody gives an argument to you, what you're doing is you're saying, look, if you accept the evidence that I'm giving you, here's some evidence. If you accept the evidence that I'm giving you, you got to accept the conclusion. So implicitly what you're saying is, especially in a deductive argument, implicitly what you're saying is if the evidence is true, so if that evidence that I gave you is actually true, then there's no way for the conclusion to be false, because we can see why that would be convincing. If there's no way that the conclusion could be false given the evidence, then if I find myself accepting evidence, it would be irrational for me to say that the conclusion is false, right? Because there's no way that it can be false. All right, so what would be an example of an argument that's like that, that it's true that if the evidence is true, then there's no way for the conclusion to be false? Well, consider the following argument. Suppose somebody gives you as part of their evidence, they tell you that, hey, if it rains outside, then the grass is wet. Okay? And then say the next piece of evidence that they give to you is that it rains outside, that it did rain outside. And what they want to get you to believe is that the grass is wet. That would be the conclusion. Well, here's our evidence. Both P1 and P2 is our evidence. P1 tells us raining guarantees that the grass is wet. Now, maybe you think that's false, but that's what it's asserting. That's what the evidence is asserting. It says raining outside guarantees that the grass outside is going to be wet. And what premise 2 tells us is it really did rain outside. So notice, if both of those end up being true, there's no way for this to be false, because premise 1 tells us that R will get you W, and premise 2 tells you did get R. Well, you better have gotten W then. All right, so why is that important for philosophers? It's important for philosophers, and really for anybody that's interested in making sure that you don't get duped or that you don't get hoodwinked by a bad argument, is it shows when it would be rational or irrational to accept a conclusion. In this particular argument, if I don't like the conclusion that the grass is wet, suppose I'm really against that for some strange reason, but I'm given this argument, then what I'm going to have to do is say that premise 1 or premise 2 is false, that at least one of those is false. But if I do accept premise 1 or premise 2, then even though I don't like the conclusion, I'm going to be forced to accept it anyways. So it gives us this framework of rationality and irrationality. It gives us this framework when I can assess whether I'm given an argument where the evidence actually supports the conclusion. It gives us this framework in which we can actually push against each other, and an objective framework at that, where we can push each other on or off a position. Okay, so another way of thinking about when an argument's evidence actually does support its conclusion is when this part holds of it. It really means the same thing that we were talking about just before, but it's another way to help you sort of think about it. So the evidence of a deductive argument actually supports its conclusion only if the following is true. Namely, when it's true of the argument that it is impossible, right? We said no way. It is impossible for both its premises to be true and its conclusion to be false. If that's an impossibility, then the evidence that you're being given by an argument really does support the conclusion. And so either you're going to end up having to accept the conclusion because you really do accept the premises, or because you don't accept the conclusion, you got to explain why one of those premises is false. Or if it turns out that they're not false, even though you don't like the conclusion, you're going to find yourself having to accept it. Right? Now, on the contrary, when is it the case that the evidence being provided by a deductive argument merely appears to support the conclusion? It does so when this is true of it. Its conclusion can be false even if all of its premises are true. So a deductive argument in which even if all of its premises are true, its conclusion could still be false, then that's one that you should not be convinced by. For all the evidence you've been given, maybe the conclusion's wrong. So let's take a look at what an example of such an argument. So the argument that we're going to look at is going to be very similar to the previous argument that we looked at. Premise 1 is our first bit of evidence. Premise 1 is going to tell us that if it rains outside, then the grass is wet. But in premise 2, instead of saying that it does rain outside, instead we're going to say that the grass is wet. And then the person who comes up and gives you this argument, what they're going to try to get you to believe, what the conclusion is going to be, is that it rained outside. So we look at the evidence here. It says it raining will guarantee that the grass is wet. And then in premise 2, we see that the grass really is wet. Maybe we go outside, we touch the grass, we feel that it's wet. Well, should we believe then that it rained? You might think so, and a lot of people are in fact confused into thinking that this is a good argument, that the evidence being given actually shows that the conclusion is got to be true. The problem is, even if it's true that it raining outside will guarantee that the grass is wet, and even if it's true that the grass is wet, it can still be false that it rained outside. Why? Well, maybe what caused the grass to be wet, so maybe what caused this to be true, is a water sprinkler. Or dew, or some other way in which the grass could be wet. So even though it didn't rain, it was the water sprinkler that made the grass wet, it would still be true that if it rained, the grass would be wet. So here we have premise 1 and premise 2 being true, but the conclusion being false. So this argument, it looks, the evidence that you're being given, it might appear to us that it supports the conclusion, but now we see that it doesn't actually support the conclusion. And first order logic can help us be able to see that. It can help us expose that. And in this case, I think the way that first order logic helps us to see that this argument doesn't actually follow is because the arrow only goes in one direction. It's only going from the direction of the R to the W. It doesn't have the arrow going from the W to the R. If it was going the other direction, right? If our first premise looked like this, instead of how it's actually written, then it would be a good argument. In the sense that the premises, the evidence really would really support the conclusion. Whether I would accept the premise to be true, that's a different story. So those are some of the ways in which first order logic is important. It laid down the foundations for modern day computers and also where AI is going to be going. It also allows us to appreciate and understand and investigate natural language a little bit better. And it also allows us to practice good philosophy and, more generally speaking, be able to understand when an argument is in fact convincing or not convincing, when the evidence actually supports the conclusion or when it merely appears to do so. And it's this last bit, this evaluating of deductive arguments, that we're going to be focusing on in this class. So we're going to be really using first order logic as a way of understanding argumentation and being able to appreciate better the relationship between evidence that's being given and the conclusion that somebody is trying to get us to buy into, or maybe that we're trying to get somebody else to buy into, or maybe what we're trying to get ourselves to buy into. So that's what we're going to be doing. I look forward to having you in this class, and I'll see you in the next video.